Engineers have been using biomimicry for years, turning to nature's time-tested solutions for fresh ideas and practical designs. From early designs mimicking fish fins to high-speed trains modeled after bird beaks, biomimicry is more than just a design trend, as it's also a cornerstone of sustainable engineering. In this video, we'll explore how biomimicry isn't just about taking cues from nature's aesthetic, but also applying deep biological principles to solve some of our toughest engineering challenges. But first, what exactly is biomimicry? Nature has long been the original blueprint for sustainable and efficient design. With over 3.8 billion years of evolution behind it, the natural world has honed solutions that balance efficiency, resilience, and harmony with the environment. Biomimicry, at its core, is the practice of studying and emulating these natural strategies to solve human design challenges. Far from a simple imitation, it involves a deep analysis of biological principles to create technologies and systems that are adaptable, resource-efficient, and environmentally friendly. Take the example of Japan's Shinkansen bullet train. When engineers were faced with the problem of a loud sonic boom as the train exited tunnels at high speeds, they turned to nature for a solution. The kingfisher, a bird that dives swiftly and quietly into water, offered an answer. By reshaping the train's nose to mimic the kingfisher's beak, engineers achieved a design that significantly reduced noise, lowered air resistance, and cut energy consumption by 15%. This real-world application of biomimicry not only enhanced the train's performance, but also proved the potential of nature-inspired designs to solve modern challenges while minimizing environmental impact. Another foundational principle in biomimicry is resource efficiency. Nature uses only what it needs. For instance, spider silk is stronger than steel by weight, yet it's produced with minimal energy and from basic proteins. Engineers and material scientists are exploring synthetic spider silk as a sustainable alternative to traditional materials, envisioning applications in everything from medical sutures to construction materials. Emulating the spider's method offers a potential pathway to strong, lightweight materials that don't rely on resource-intensive manufacturing processes. Adaptability is another hallmark of natural systems. Coral reefs, for example, thrive in harsh environments, constantly adapting to fluctuating ocean temperatures and acidity. Engineers are studying these mechanisms to design building materials and environmental sensors that can withstand extreme conditions. Biomimetic is about creating structures and systems that work with their surroundings, dynamically responding to environmental stresses rather than resisting them. Finally, resilience is embedded in every aspect of the natural world. Ecosystems are interconnected, resilient networks that can recover from disruptions. This concept has inspired engineers to design infrastructure that isn't just strong, but able to self-heal or adapt under stress. For instance, researchers are developing self-healing concrete by incorporating bacteria that activate and produce calcium carbonate when cracks form. This material, inspired by biological resilience, could reduce maintenance costs and extend the lifespan of roads and buildings, ultimately conserving resources and reducing waste. Let's look at structural mimicry next. Nature's ability to optimize structural design is unparalleled. From the delicate yet powerful architecture of shells to the complex networks of tree branches, natural forms have evolved over millions of years to maximize strength, minimize material usage, and adapt to environmental demands. Structural biomimicry is all about tapping into these natural blueprints to create efficient, sustainable, and resilient designs for human structures, such as buildings, bridges, and other infrastructure. Take the honeycomb, for instance. The hexagonal cells of a beehive are one of nature's most efficient shapes, packing the maximum amount of space with the least amount of material. This structure is incredibly strong for its size, providing both stability and lightness. Engineers have applied this principle to a range of applications, including lightweight, strong materials for construction. One notable example is the Eden project in the UK, a series of geodesic domes that house biodomes mimicking different global climates. The geodesic design, inspired by the structure of pollen grains and other natural forms, offers strength and stability while using far less material than traditional buildings of similar size and shape. These domes are not only a feat of engineering, but also an exemplary case of biomimetic architecture, where efficiency and environmental consciousness intersect. Another iconic example of structural biomimicry can be seen in the Lotus Temple in India. The building's unique design mimics the petals of the lotus flower, a symbol of purity and beauty in many cultures. But beyond its aesthetic appeal, the structure's form offers practical advantages in terms of aerodynamics and natural ventilation. The petal-like shapes, made of white marble, are arranged in such a way that they optimize airflow, keeping the interior cooler in the hot, humid climate of Delhi. This natural cooling effect reduces the need for air conditioning, promoting energy efficiency and sustainability. One of the more recent innovations in structural biomimicry comes from self-healing materials, which take their cue from biological systems that can repair themselves. The idea is inspired by how plants and animals heal wounds. For example, self-healing concrete contains capsules of bacteria that activate when cracks form, producing calcium carbonate to seal up the cracks and prevent further damage. This technology, although still developing, promises to reduce the need for frequent repairs and maintenance, extending the lifespan of infrastructure while cutting down on resource usage. Then there's the application of structural optimization, inspired by natural growth patterns. Bone, for example, is a remarkable material. It is both lightweight and strong, designed to bear weight without being overly dense. The trabecular structure of bone, its spongy, porous nature, is an example of how natural systems achieve high strength-to-weight ratios. Engineers are studying this pattern to design lighter, more efficient materials for everything from aerospace components to automotive structures. The study of fractals in nature, such as the branching of trees or the pattern of blood vessels, has also inspired the development of highly efficient, self-supporting structures that are both flexible and strong. In the world of architecture, biomimetic design is not just about mimicking shapes and structures, but also about integrating nature's principles of resilience and sustainability. Natural structures are designed to endure and adapt to changing conditions. For example, termite mounds in Africa maintain a consistent internal temperature despite extreme external fluctuations. This self-regulation inspired the design of natural cooling systems in buildings. By mimicking termite mounds, architects have created buildings that stay cool without relying on traditional air conditioning, reducing energy consumption and lowering environmental impact. When it comes to moving efficiently through air and water, nature has refined its designs over millions of years. By observing the sleek forms and efficient movements of birds, fish, and other animals, engineers have found innovative ways to apply nature's principles of aerodynamics and hydrodynamics to human technology, optimizing performance, reducing resistance, and improving energy efficiency across various fields. One of the most direct applications of biomimicry and fluid dynamics is in aviation. Birds, particularly large soaring species like eagles, have wingtips that curve upward, a structure that reduces air resistance and minimizes energy loss. These winglets reduce drag by altering the way air flows over the wing, allowing birds to fly longer distances without tiring. Engineers have applied this concept to commercial aircraft design, leading to the development of winglets on the tips of airplane wings. Winglets reduce the vortices that form as air moves over the wing, which helps decrease drag and improve fuel efficiency. Studies by Boeing and Airbus have shown that winglets can save up to 5% of fuel on long-haul flights, a significant reduction in both fuel costs and environmental impact. Similarly, whale fins have provided inspiration for advances in wind turbine blade design. The humpback whale's pectoral fins have unique rounded bumps called tubercles along their leading edges. These bumps help whales maneuver with remarkable agility despite their massive size, as they reduce drag and increase lift by channeling the water flow across the fins in a more efficient manner. Engineers at companies like Whale Power have applied this principle to wind turbine blades, adding tubercles along the blade edges. This design improves airflow over the blades, allowing them to capture more energy and operate effectively at lower wind speeds. Studies have shown that turbine blades with these biomimetic features can produce up to 20% more energy than traditional designs. In the world of ground vehicles, biomimicry and fluid dynamics has also influenced the design of high-speed trains. Japan's Shinkansen bullet train, known for its speed and quietness, encountered a challenge early on. The pressure waves created by the train as it exited tunnels caused loud, disruptive noise. Engineers found a solution by studying the kingfisher, a bird known for diving into water with minimal splash due to its pointed beak. By reshaping the front of the train to mimic the kingfisher's beak, they not only reduced tunnel boom, but also decreased air resistance, resulting in a quieter, faster, and more energy-efficient train. One of the most exciting aspects of biomimetic fluid dynamics is its potential for innovation in underwater robotics. Inspired by the way fish move, researchers are designing robots that can swim efficiently through water with minimal noise, a key advantage for research and exploration where stealth and precision are needed. Robotic fish like the MIT-designed SOFI mimic the flexible movement of fishtails, using fluid dynamics to move quietly and efficiently in water. This approach offers significant advantages over traditional propellers, which create noise and turbulence, disturbing marine life. When we look to nature for solutions to our energy needs, we see that ecosystems have developed their own renewable cycles, capturing energy efficiently and sustainably. By emulating these natural processes, engineers are pioneering renewable energy solutions that push us closer to a future of accessible, eco-friendly energy. One of the most iconic examples of nature-inspired renewable energy is solar technology. Plants have been perfecting the art of capturing sunlight for billions of years through photosynthesis, converting it into energy that powers life on Earth. Inspired by this process, scientists developed artificial photosynthesis, which aims to mimic plants' ability to convert sunlight, water, and carbon dioxide into energy-rich fuels like hydrogen. By creating synthetic leaves, researchers hope to produce hydrogen fuel in a way that's clean, renewable, and highly efficient. This approach could offer a viable alternative to fossil fuels, creating an energy source that doesn't emit greenhouse gases. In solar panel design, engineers have drawn inspiration from the surface of lotus leaves, known for their superhydrophobic, self-cleaning properties. Lotus leaves repel water and dust, ensuring that photosynthesis can occur efficiently without interference from particles. Solar panels with a similar coating can stay clean for longer, maintaining their efficiency even in dusty or arid environments. This self-cleaning design, inspired by nature's own solutions, reduces the need for water and labor to maintain solar arrays, enhancing the sustainability and viability of solar power in challenging climates. Wind energy has also benefited from nature-inspired advancements. The whale's pectoral fins, with their unique tubercle structures, have been applied to the design of wind turbine blades, improving their aerodynamics. These tubercle-enhanced blades help to increase lift and reduce drag, making the turbines more efficient and allowing them to operate at lower wind speeds. As wind energy continues to expand, especially in regions with variable wind conditions, this biomimetic approach holds promise for making turbines more productive and versatile. In geothermal energy, nature's underground heat sources have inspired more efficient ways to tap into Earth's internal heat. Geothermal energy systems are essentially enhanced versions of Earth's natural geysers and hot springs, which channel heat from deep below the surface. Engineers have studied these natural systems to improve how we harness geothermal energy, using heat exchange methods that pull energy from the Earth's crust without damaging its structure. By observing how natural hot springs efficiently transfer heat, geothermal engineers have developed systems that minimize environmental impact while providing a steady, renewable source of power. Another innovative area is bio-inspired fuel cells. In living organisms, cells use enzymes to produce energy through chemical reactions. Engineers working on biofuel cells have developed designs that use enzymes as catalysts, producing electricity by breaking down sugars, much like cells do. These bio-inspired fuel cells promise to generate power in a highly efficient, low-impact way, potentially fueling everything from small electronics to vehicles without relying on combustion or harmful emissions. In the world of biotechnology and materials science, nature has served as a vast sourcebook of solutions. By replicating natural materials and processes, scientists and engineers are crafting products that are not only durable and adaptive, but also often biodegradable and eco-friendly. These breakthroughs are leading us toward a future where human industry can support rather than harm the environment, reflecting the resourcefulness of ecosystems that have optimized materials over billions of years. One of the most impressive examples in this field is synthetic spider silk. Spider silk, pound for pound, is stronger than steel and far more flexible, making it one of nature's strongest materials. Researchers have worked tirelessly to replicate spider silk in laboratories, creating synthetic versions that could transform both medicine and industry. Lightweight, biodegradable, and extraordinarily strong, synthetic spider silk has potential applications in creating medical sutures, soft tissue repair materials, and even lightweight armor. The quest to produce it at scale has already led to advancements in genetic engineering, as scientists use modified bacteria, yeast, or even plants to produce spider silk proteins in large quantities, paving the way for this wonder material's widespread use. The self-healing properties of skin and plant tissues have also inspired innovation in materials science. Imagine a car bumper or a smartphone screen that can heal itself after being scratched or damaged. Inspired by how plants and animals repair wounds, scientists have created polymers and coatings that can autonomously repair minor damages. One example is a synthetic material inspired by squid ring teeth proteins, which exhibit self-healing properties when exposed to water. These self-repairing materials have huge implications for reducing waste and extending the life of products, from electronics to construction materials, by minimizing the need for replacements. Another area where nature's chemistry is making waves is in biodegradable plastics. Conventional plastics, derived from petrochemicals, are notorious for their environmental impact, persisting in ecosystems for hundreds of years. By studying natural polymers found in plants and animals, scientists have developed biodegradable alternatives that can break down safely after use. One example is chitosan, a material derived from the shells of crustaceans, like shrimp and crabs. Chitosan has shown promise as a replacement for conventional plastic packaging, as it naturally decomposes in the environment and is even edible. This biomaterial aligns with nature's principle of waste-free cycles, where materials decompose and return to the earth without harming ecosystems. The lotus effect has influenced the creation of self-cleaning materials in both biotechnology and materials science. Lotus leaves have a unique surface structure that repels water and dirt, keeping them clean even in muddy environments. This property has inspired self-cleaning coatings for glass, textiles, and paints. These coatings reduce maintenance needs, save water, and extend product life by preventing the buildup of grime and reducing the need for harsh cleaning chemicals. For instance, glass treated with a lotus-inspired coating can stay clear for longer, enhancing visibility in windows and solar panels and boosting efficiency without requiring frequent cleaning. In robotics, engineers are turning to the animal kingdom to build machines that move and adapt to their environments with a level of agility and resilience previously thought impossible. Nature's designs, honed over millions of years, offer incredible insights into efficient movement, balance, and adaptability, making them ideal models for robots meant to operate in unpredictable, rugged environments. One of the most notable examples in biomimetic robotics is Boston Dynamics' Big Dog, a four-legged robot designed to handle rough terrain. Inspired by the agility and balance of quadrupeds, Big Dog can navigate challenging landscapes with surprising stability. Unlike traditional wheeled or tracked robots, which struggle on uneven ground, Big Dog uses advanced algorithms to mimic the coordinated, reflexive movements of animals. It can remain stable even when pushed, just like a real animal would adjust to maintain its footing. This stability makes it an excellent candidate for tasks that require traversing complex terrains, such as delivering supplies to remote military outposts or assisting in search and rescue operations in disaster-stricken areas. In the quest to replicate nature's speed and agility, cheetahs have also become a focal point of robotic research. MIT's Mini Cheetah, a robot designed to replicate the feline speed and flexibility, showcases impressive maneuverability and can run at speeds over 9 miles per hour. Its lightweight, compact design allows it to make sharp turns, roll over, and even land on its feet after a fall, behaviors that are essential for handling unpredictable environments. The Mini Cheetah's design represents a leap forward in robotics, offering a model for robots that may one day assist in dangerous or dynamic settings like construction sites, search and rescue operations, and agricultural fields where adaptability to the terrain is key. The biomimicry approach has also extended into robotic drones that draw inspiration from birds and insects. Nature's flying organisms are experts in energy-efficient flight, with adaptations that allow them to glide, hover, and even recover from turbulent air currents. Inspired by these mechanisms, roboticists are developing drones that can maneuver through forests, cities, or even small indoor spaces with a natural, fluid motion. For instance, the University of Pennsylvania's RoboBee mimics the flapping wing flight of bees, allowing it to hover and make precise movements. This bio-inspired drone design opens possibilities for pollinating crops, inspecting hard-to-reach areas, or even conducting surveillance in hazardous zones. Even the biomechanics of fish are proving influential, especially in underwater robotics. Fish have evolved streamlined bodies and tail movements that allow for efficient, agile swimming. Inspired by this, the development of bio-inspired underwater drones, like the RoboFish, aims to revolutionize underwater exploration. The RoboFish's tail is designed to mimic the side-to-side movement of a fish's tail, making it quieter and more efficient than traditional propellers. These underwater robots can be used in marine biology to monitor fish populations without disturbing ecosystems, conduct pipeline inspections, or explore shipwrecks and underwater caverns where maneuverability and low environmental impact are essential. Biomimicry is not just about creating innovative technologies. It's also about using nature's design principles to mitigate humanity's environmental footprint. By looking to nature's time-tested solutions, engineers and designers are developing eco-friendly systems and materials that reduce waste, conserve resources, and promote sustainability. Biomimicry presents a profound opportunity to move away from destructive industrial practices and toward models that work in harmony with the environment, echoing nature's own strategies for balance and regeneration. One notable example of this is sustainable packaging. Inspired by the peel structure of fruits and vegetables, engineers are developing new biodegradable packaging solutions that can decompose naturally, reducing our reliance on single-use plastics. The design of fruit and vegetable peels offers a clear lesson in resource efficiency. The peels are strong enough to protect the contents inside, but are also completely biodegradable. By mimicking this natural approach, companies are creating packaging that doesn't burden landfills or ecosystems. Such innovations are vital in reducing plastic pollution, which has reached crisis levels worldwide. Products like eco-friendly packaging made from seaweed or mushroom-based materials are gaining traction, offering an alternative to petroleum-based plastic. Another area where biomimicry is having a significant environmental impact is in building design. Nature has perfected the art of resource efficiency, and buildings inspired by natural cooling methods are leading the charge in sustainable architecture. One prime example is the design of termite mounds. Termites live in large colonies and build towering mounds with complex internal tunnels that maintain a steady temperature, even in hot climates. The structure's ventilation system regulates temperature by drawing in cooler air and expelling warm air, keeping the mound's interior temperature stable without the need for energy-intensive cooling systems. Engineers and architects have applied this concept to eco-friendly buildings, most notably in the design of the Eastgate Center in Harare, Zimbabwe, which uses natural ventilation inspired by termite mounds to maintain a comfortable temperature. This building requires only a fraction of the energy that traditional air-conditioned buildings would need to maintain the same comfort levels. By adopting nature-inspired cooling strategies, these buildings not only minimize energy consumption, but also reduce the carbon footprint associated with construction and daily operations. Beyond energy conservation, biomimicry also addresses critical global challenges like carbon sequestration, the process of capturing and storing atmospheric carbon dioxide to mitigate climate change. Engineers are turning to natural carbon sinks, like coral reefs, to inspire innovative solutions. Coral reefs naturally absorb carbon dioxide through their calcium carbonate structures, creating a carbon sink while supporting rich biodiversity. Researchers are exploring ways to replicate this process by developing carbon capture technologies that mimic the biochemical processes in coral. Such innovations hold promise for large-scale carbon capture and storage systems that can mitigate the impacts of rising CO2 levels in the atmosphere. Water conservation is another field where biomimicry is making strides. One example of this is the Namib desert beetle, which has evolved a unique method of collecting water from fog. The beetle's back has hydrophilic and hydrophobic patterns that allow it to collect water from the air, which then drips down to its mouth. Engineers have studied this technique to create self-watering surfaces that capture water from the atmosphere for use in arid regions. These designs are being integrated into water collection systems, agricultural irrigation methods, and even personal hydration devices. Biomimicry in waste management also offers transformative potential. Nature never creates waste. Everything in ecosystems is reused and recycled. Inspired by this, Engineers are developing closed-loop systems where waste products from one process are used as raw materials for another. A notable example is the design of waste-to-energy systems that mimic natural nutrient cycling. These systems aim to reduce industrial waste by converting it into energy or other useful byproducts. This circular approach helps conserve resources and reduce the environmental burden of linear production models, where raw materials are used once and discarded. And that's a look at how biomimicry is transforming engineering by bringing nature's innovations into our technology. If you enjoyed this journey into nature-inspired design, don't forget to like, subscribe, and turn on notifications for more insights into the future of engineering and technology. Drop a comment below with your thoughts and let us know what you would like us to cover next. Thanks for watching, and we'll see you in the next video.